everyone. I welcome you all to the Rubber Industry News Server. This is a Technobiz weekly online program for the global rubber industry. Rubber Industry News Server has technical talks, panel discussions, and a business conversation or leadership conversations on every Monday. I welcome you all. Today, we are on the episode number 41. And I welcome you to this episode number 41. In this episode, we have a technical talk on the micro compounder for rubber research and development, introduction and case studies. This presentation is given by Dr. Guralp Koch, is a Chief Technology Officer, Explore Instruments based in Netherlands. Before I invite Dr. Guralp, let me brief you about the Technobiz. Technobiz, based in Thailand, established in 2005, and it is recognized as International Resource Center for Industries and Technologies. Two main services, one is a professional education, other is a business services. When it comes to services, we organize trade exhibitions, training, conferences, roadshows, network events, virtual events. We also have publications, and we have knowledge test, factory process audit, technical consulting, marketing and branding. So we have a wide range of service, all connected to the education and the business development. When it comes to the business focus, we have two segments in business focus. One is a polymer, other one is non-polymer. The polymer we cover on the rubber, latex and tire, plastics and composites, polyurethane foams, adhesives and coatings. In non-polymer, we focus on energy, environment, water membranes, filtration and separation, and other chemical processes. We provide pretty much global services. Let me brief you about what kind of services we offer for the rubber, latex and tire industries. We organize an exhibition called a GRTE, Global Rubber Latex and Tire Expo 5th edition. This 5th edition will be held in Bangkok next year, 29th to 31st March at BITEC. This is recognized as the gateway to global markets and the knowledge hub for rubber, latex and tire industries. It is a must attend event for all the rubber and tire industry professionals for the GRTE. You can check more details at the expo.technobiz.org. We also organize exhibition in the Middle East Rubber and Tire Expo. This is second edition next year during the 21st to 22nd November in Sharjah, United Arab Emirates. Sharjah is located very close to Dubai. So both these events, we have also rubber research and patents poster fair. We promote research at these exhibitions. The reason is research is one of the important backbone of the industry growth. So we bring the researchers and industries to exchange information and also explore collaboration and cooperation. We offer online training programs, rubber industry online training through our know-how webinar project. Know-how, you can check more details about it, know-how-webinars.com. Currently, we have more than 40 experts from different parts of the world are contributing this online training program. They are well experienced and knowledgeable, and they are the resource person for these online training programs. These online training programs, we have close to 250 short topics, which are 30 minutes to 3 hours long. We also have a master classes, more than 30 plus master classes, which are 1 day to 10 day long. And we're offering a diploma program 3 month long, which is basically executive diploma 360 degrees on rubber industry technology and management. This is focused on the non-tire industry. We don't include tire or latex. It's a purely non-tire industry. It's a 3 month long program. We have books, publications. We publish reference books and also pocket books for the benefit of the rubber industries. As you know, this Rubber Industry News Server, this is a weekly program on every Monday where we have inviting experts to do technical talks or market outlooks or panel discussions and conversation. We are introducing the Latex Industry News Server starting this week. It's a fortnightly online program for the global rubber industry. Here also, that this is purely focused on the latex industry, dip and non-dip latex products. Again, this also has technical talks, panel discussions, and business conversations. We have a Rubber Industry Connect, and this is basically a digital marketing platform for the rubber industries, where we promote technologies and products through the social media platforms managed by Technobiz to the global markets. We have a Rubber Industry Roadshows. These are basically meet and greet events, which we're going to host next year onwards, where you can have local networking events. Currently, we're working on the Rubber Industry Digital Library, which is going to be a valuable asset for all the rubber industry. And it will have a literature resource. We have technical papers, articles, brochures, all the presentations. Everybody can post their information in this library so that company can access the useful information through this digital library. The work in progress, you can always check more details at the library.technobiz.org. We are pretty much active on social media platform, currently followed by more than 20,000 followers in various platforms, LinkedIn, WhatsApp, Twitter, and also Facebook. All of them rubber and tire industry professionals. We have a video platform on YouTube, the Technobiz channel. There's a Rubber Industry News. So most of the Rubber Industry News our subscribers are following on the YouTube channel, Technobiz, because we post the recorded version of this session next day of the live session. Other than that, we have various consulting services, technical consulting, process improvement audits, and also marketing, promotional, branding activities. Okay, that's about the the activities of Technobiz. I invite all of you to this event, IRC 2022, which will be held during the 24th to 26th November in Bangalore, in India. And this is it has the conference, a couple of workshops, and also an exhibition. An International Rubber Conference is organized by the Indian Rubber Institute. You can check more information at the irc2022.com. If you'd like to register, please do so. There are more than 120 speakers participating in this conference, IRC 2022. It's a must-attend event as well. Please do check the website, irc2022.com. Okay, that's about Technobiz, what we do. I'm hoping that you get a clear idea about what kind of services we offer for the rubber industries. And so if you need more information, you can always connect me, contact me. I think most of you have my contact information. Feel free to check it out. Okay, let's welcome you all to the today's episode number 41 of the Rubber Industry News Hour. In this one, we have Dr. Gaurav Koch, is a Chief Technology Officer from Explore Instruments from the Netherlands. He'll be presenting on the micro compounders for rubber research and development, introduction and case studies. Dr. Gaurav is a specialized person with huge expertise, both the practical as well as research experience, and he specializes on the polymer compounding, polymer blending, nanocomposites, and elastomeric rubber compounds, and also the biodegradable and biomedical materials. So let's invite Dr. Gaurav to make a presentation on the micro compounders for rubber R&D, introduction and case studies.
Hello, ladies and gentlemen. This is Güral Pözkoç from Explore Instruments company. Today, I'm going to talk about microcompounders, and my intention is to give you a flavor about how a microcompounder can serve as a mixing tool for rubber research and development. I think it would be good to start with a short biography of myself. Currently, I am the Chief Technology Officer and Managing Director at Explore Instruments, which is located in the Netherlands. I am responsible for the R&D department and the management of the production and daily operations of the company. I have a Bachelor of Science degree in Chemical Engineering and a PhD degree in Polymer Science and Technology. My area of focus is polymer compounding, polymer blends, composites, and nanocomposites. Currently, I'm also a professor at Istinye University, Department of Chemical Engineering. Xplore is a technology company producing lab-scale polymer processing instruments. We are located in southern part of Netherlands, which is between Germany and Belgium. Xplore started in the 90s to develop and build unique processing instruments for the R&D department of DSM, which is a commodity and engineering plastics company. Since March 2014, Xplore has become a fully independent, privately owned company, officially named Xplore Instruments BV. This enables us to be even more dedicated to our core business, helping our R&D customers by developing, manufacturing, and marketing the best microprocessing and post-die shaping equipments in the world. At the beginning, I think it will be good to start with an introduction to the microcompounders to get familiar. The term microcompounding is not an invented technical word, but an anonymous word that was born and accepted by the research community. Microcompounding refers to the mixing of processing of polymers, mostly thermoplastics, to make formulations in the molten state on a very small scale, typically several milliliters. Microcompounders are tabletop mini extruders having parallel twin screws, or counter-rotating and fully intermeshing. The batch volume can be varied between 3 cc to 40 cc. The core of the compounder is a vertically positioned liquid-tight barrel with two easily detachable conical mixing screws. Both screws and housing are specially engineered to minimize wear and to resist chemicals in a wide range of temperature. The robust design ensures the generation of reproducible and stable data for years, and the vertical position of the liquid-tight barrel allows the processing of low viscous fluids down to 10 Pascal seconds. The screw speed can be set between 1 RPM to 500 RPM, and the barrel temperature can go up to 500 C. We have 40 Newton meters of torque over 15 milliliters of material volume. The basic feature of these compounders is the ability to recirculate the molten content during the mixing time. Therefore, actually, they are batch mixers. State-of-the-art microcompounders have a batch mode, which is so-called recirculation, and a conical shape. How does this recirculation channel work? When we feed the polymer, it can be in granular form or in powder form. It's taken down by the screws into the barrel. There it melts with the help of the heated barrel and the friction of the screws. Then the melt is sheared and pressurized through the down part of the microcompounder. Here, there's a valve that guides the melt through the recirculation channel to the top, and the melt is again entered into the shear zone. And in this way, the mixing can be sustained. The number of the pass is defined by the time that you keep the valve closed. Once you open the valve, the melt flows out. In a parallel twin screw extruder, the residence time is controlled by L/D ratio of the screw and the screw geometry. Here, it's controlled by the time. What are the benefits of working with a microcompounder? Imagine you want to make a formulation optimization study and design of experiment set 10 to 15 different formulations. Then you need nearly 1 week to finish the experiments if you use a 30 millimeter lab scale parallel twin screw extruder. And you probably need 2 lab technicians and a minimum of 50 kilograms of material for each batch. However, if you use a microcompounder, you can finish these 15 different new formulations in 1 day using 500 grams of material with only 1 technician. This means that you are fast in the first step of the research and your R&D costs are lower. Besides, it's easy to operate, easy to clean, and proven that it's a super mixer. In Explore Microcompounder, while you are processing your material, it's also possible to retrieve inline rheological data, such as viscosity, the shear rate, mechanical energy input, die pressure. This is possible since we have a dedicated rheological model of the compounder which provides us to generate these data. By using this option, researchers can track the changes of the molecular structure of their material in situ. If we particularly focus on the rubber compounding, you can follow the mastication process, for example, or you can follow any possible marching or scorching in your compound. We believe that it's a very useful tool for rubber compound development. The torque of a microcompounder is a key parameter to have successful mixing. In order to be in line with the current high viscous materials, Explore developed a high torque microcompounder which has 40 Newton meters of torque per 15 cubic centimeter of melt. To be honest, at that time, this much of torque was more than enough for the processing of thermoplastics. But having such kind of an option made us to think if we could process rubbers in our new high torque microcompounder. Although we foresee some challenges already. In the upcoming part of my presentation, I will summarize 3 case studies in which microcompounders were used to prepare the rubber compounds. And my aim is to pull your attention toward the potential uses of Explore microcompounder in novel emerging areas of rubber compound development. In the first study, you will see some data regarding the comparison of microcompounders with conventional Banbury mixers in terms of dispersion and dispersion-related properties, such as mechanical properties and rheology. For this purpose, we designed 2 recipes based on EPDM silica and EPDM carbon black. Here one should note that the mixing of carbon black into EPDM is much more favorable than those of silica due to its chemical compatibility, whereas dispersing silica in EPDM is challenging since the polarity of silica is different than EPDM. We have followed a sequential mixing route for the conventional mixing part in a 400 cc Banbury mixer. The total mixing time, including the twin roll milling, was 15 minutes. On the other hand, we prepared the same compounds using a microcompounder which was operated at 25 or 100 RPM at 80 degrees Celsius and for only 3 minutes total mixing time. It's important to note that both processing methods were not optimized for the compounding of EPDM using silica or carbon black. In these videos, you can see the important steps of compounding process using the microcompounder. In the first video, on the left top, you see that the feeding of the rubber chunks and the additives such as fillers, oil, or cross-linking system is relatively easy. Please note that, as in conventional processing, we first masticate the rubber with oil and the fillers. Then, in the last part of the compounding, we normally add the cross-linking system. At the end of the compounding process, you can extrude the content by turning on the valve of the barrel. You can either extrude in a container or you can use our conveyor belt to take the extrudate easily. Now, let us look at the dispersion of compounds prepared in different mixers. You can see from the disper grader images that the dispersion of both carbon black and silica fillers is satisfactory for all cases. Generally, the dispersion of carbon black and silica in a polymer matrix is related to reducing the size of carbon black or silica in the form of aggregates. It was obtained for EPDM silica compounds that the dispersion of silica in EPDM was much better in the compounds prepared with microcompounder compared to the Banbury mixer. Moreover, the average particle size of silica degrees significantly from 10 microns to 5 microns level. The dispersion quality percentage of silica was much better in the composites prepared in microcompounder. Similar test results were also obtained for EPDM carbon black composites. Please remind that these two types of mixing were not optimized to get best mixing. However, we experienced before that these two routes work well for similar mixtures. The other important parameter is seen to be the screw speed in microcompounder, which enhanced the dispersion of the carbon black filler positively in EPDM when we go from 25 RPM to 100 RPM. On the other hand, increasing screw speed did not influence the dispersion of silica that much, since the dispersion process of silica in EPDM is thermodynamically driven. We also conducted scanning electron microscopy analysis in order to further investigate the dispersion of the fillers in the matrix. Some analysis showed a homogeneous dispersion of the fillers in the EPDM matrix when both mixing methods were applied. As can be seen in figures, that carbon black dispersed homogeneously in the matrix independent of the sample preparation method. On the other hand, agglomerated silica particles were obtained compared to carbon black due to the challenging dispersion of the silica in EPDM. For EPDM silica compounds prepared in Banbury, silica dispersion was found to be coarser. The particle size of silica in EPDM ranged from 10 to 100 microns. On the other hand, the compounding of EPDM silica compounds in microcompounder at small RPMs led to a decrease in the diameter of silica agglomerates. The average diameter of silica was found to be 20 microns. Moreover, a significant improvement in the dispersion of silica in EPDM compounds prepared in microcompounder at higher RPMs was obtained, as shown in the figures on the right-hand side. Of course, the level of dispersion has an impact on the resulting mechanical properties of the vulcanized samples. The mechanical properties of EPDM compounds were represented in the figures in the slide. Tensile strength data revealed that the tensile strength obtained from microcompounder was higher than that of Banbury. This was possibly due to the better dispersion of the fillers, both carbon black and silica. The increasing RPM in the microcompounder from 25 to 100 resulted in improved tensile strength independent from filler type. As Banbury and microcompounder were compared, the difference obtained from silica was more significant than that of carbon black due to the better dispersion. Additionally, the scatter of the data obtained from microcompounder was lower than that of Banbury due to better homogenization of the sample batches, as discussed in the dispergrader test results. A similar trend was also observed for elongation at black values. The interfacial interaction between polymer matrix and fillers was a much more effective criteria for higher tensile strength and elongation at break values in particle reinforced polymer composites. The interfacial interaction between filler and matrix and the interaction between filler and other combinations of components such as accelerator and activators and the level of dispersion of the fillers in rubber matrix were significant parameters to obtain improvement in tensile strength of rubber-based composite materials. Therefore, higher elongation at break and tensile strength values of both EPDM carbon black and EPDM silica compounds was due to the finer dispersion of filler in EPDM, which were prepared in microcompounder. The next example that I would like to share is based on a tire thread compound, including carbon nanotubes. Our aim was to improve the mechanical properties of the tire by the incorporation of carbon nanotubes due to their high aspect ratio that would lead to a longer lifetime of a tire. As you know, carbon nanotubes are one of the expensive additives to use in regular compound development. Therefore, in this study, we have utilized a microcompounder to screen the properties of the recipes prepared using carbon nanotubes. These are the recipes that we prepared. The matrix was based on a NR-SPR blend, which is reinforced with 30 PHR carbon black. The carbon nanotube content was changing from 0, 3, and 7 PHR by replacing with the corresponding amount of carbon black. The rest of the recipe was kept constant. We have prepared the compounds in a micro compounder, as I already mentioned. The processing conditions are shown here. We only mixed 2 minutes with cross-linking system, without cross-linking system, and 1 minute with the cross-linking system, in total 3 minutes. At the end of compounding process, the compound was dumped in a mold and cross-linked according to the data which was obtained from moving tire rheometer results. We analyzed the dispersion of the fillers using dispergrader and electron microscopy. When we focus on the dispersion, we don't observe any agglomeration of the fillers or obvious phase separation of the matrix, which is NR and SPR. The homogeneity of the samples was good. The presence of carbon nanotube did not significantly influence the dispersion level of carbon black. However, carbon nanotubes are not visible at these magnifications. At 5,000 magnification, we can observe the carbon nanotubes individually, but still the carbon black particles are not distinctly visible. In addition, any aggregates of carbon nanotube or carbon black are not visible at the nano level as well. These results show that the microcompounding resulted in a homogeneous filler distribution in 3 minutes of mixing at both micro and nanoscale. The existence of high aspect ratio fillers like carbon nanotubes is known to be effective in the curing behavior of rubber compounds. In order to check this, we performed moving tire rheometer analysis and DSC experiments. We observed from DSC that the presence of carbon nanotubes increased onset and peak temperatures of the curing exotherm, as you can see. In other words, it results in a delay in curing behavior. This can be due to the barrier effect of carbon nanotubes against the diffusion of reactive groups that sustain the vulcanization reaction. A complementary behavior was also observed from moving tire rheometer results, indicating that the cross-linking reaction was retarded by the presence of carbon nanotube. In addition, cross-linking density first dropped by the addition of carbon nanotubes, but then increased at 7%. T90 values increased by the increase in carbon nanotube content. This can be due to the barrier effect of carbon nanotube against the diffusion of the chemical species that are involved in cross-linking reaction. However, if enough time is given, one could obtain a fully cross-linked structure. Similar to that, cure rate extent, which is associated with the cross-link density, first dropped, then increased at 7 PHR carbon nanotube content. This was also supported by Fleury-Rehner swelling measurements and TSSR measurements. As we look at the mechanical properties, although the cross-linking density dropped at 3 PHR carbon nanotube addition, we observed a slight increase in tensile strength, but an eye-catching jump at 7 PHR carbon nanotube. In order to further understand the dispersion mechanism of carbon nanotube and carbon black, we conducted electrical resistivity and thermal conductivity measurements. In both cases, the conductivity of the sample increased drastically at 7 PHR carbon nanotube content. The increase in thermal conductivity also explains the increase in cross-linking density due to better homogenization of the heat during the vulcanization reaction. As a result of the formation of the network structure and the higher cross-linking density, we observed better mechanical properties at 7 PHR carbon nanotube content. Last but not least, we recently worked on a project with 2 universities on a tire company to develop self-healable rubber compounds using chemically modified polyhedral oligomeric silsescoxane-based nanocomposites. As you know that one of the important concerns regarding the tire industry is rubber waste. In this respect, the successful design of self-healable rubber compounds can extend the lifetime of a tire. Self-healable rubber compounds have been investigated by many researchers till now. The common approach is to use an additive that provides the healing of polymer molecule through re-physical or covalent bonding of the molecules. In this study, we have also used the same approach, but this time we used a nanopose structure having chemical functional groups that can sustain covalently and hydrogen bonding. We have focused on the inner liner compound, which is composed of brominated butyl rubber. We used 3 different pose compositions ranging from 3 to 7 PHR pose in the rubber matrix. The mixing was carried out in a high torque microcompounder at ATC. The screw speed was 100 RPM and the total mixing time was 3 minutes. After cross-linking, the samples were cured in a hot press, and then the dumbbell-shaped samples were punched from the cured sheets for self-healing tests. In order to investigate the self-healing properties, we cut the dumbbell shape into 2 pieces using scissors, then brought 2 parts together from the wounded part. As a stimulus, we applied temperature ranging from room temperature to 120 C for different application times. In these 2 figures on top, you can see the self-healed tensile properties of brominated butyl rubber samples with respect to temperature and time. As you see that increasing time and temperature increase the healing properties of brominated rubber in any conditions. As the pose content increased, the healing properties also increased. We observed a maximum at 5 PHR pose for both elongation and strength. SEM imaging studies were performed on the samples having joint surfaces. In these micrographs, you can see that by increasing time, the cut trace was found to be disappeared, indicating that the 2 wound surfaces were conjugated. We also performed an elemental analysis via energy dispersive X-ray spectrometry at the wound site to observe the distribution of the pose and vulcanizing agents. As you see here that both pose distribution and sulfur distribution are homogeneous at the wound lips after healing process. Now the conclusion. We have demonstrated with the presented promising results that microcompounders can successfully mix conventional additives like carbon black, silica, and nano additives like carbon nanotubes and pose into rubbers. Lab-scale mixing devices, which serve as cost and time-effective research tools, provide possibilities for processing a few grams of material. They have the capability of batch processing rubbers with a similar shear and thermal environment as conventional internal mixers. These micro devices can be used as fast screening tools in the field of rubber-based formulation development to speed up the initial phases of R&D processes. At Explore, we aim to facilitate the researchers in evaluating their new ideas through reliable and fast screening of many samples at minimum costs, which are scalable to production sizes. In this way, Explore supports the quality and speed of rubber innovation in many fields of different material R&D process. While finishing my talk, I would like to thank Professor Kodal and his research fellows for contributing our R&D works on microcompounding of rubbers. For further information regarding our product portfolio, please refer to our webpage, and please feel free to contact us to book a demo to process your challenging rubber compounds in our microcompounders. Thank you very much.
That's a presentation on the microcompounders for rubber research and development, introduction and case studies. So Dr. Gaurav is here to answer any questions you have. So yeah, we already have some questions, so let me put onto the screen. Dr. Gaurav, is it all right with you? Okay, so I will put your questions. I will put questions onto the screen and you address them one by one. Yeah. Here we go.
Yeah, okay. What do you think the ultimate impact of microcompounding technology on the rubber industry would be? Okay. Interesting question. Yeah. Before answering that question, I would like to first elaborate on where we can locate the microcompounding technology in the total R&D commercialization process. The first step is the idea generation. We brainstorm to come up with many possible ideas. Then we have to screen those ideas by considering relevant commercial and technical, or let's say scientific facts. And then we have to test those ideas to come with a short list. At this stage, microcompounders play a critical role in rubber product development. When you use a microcompounder, the step at which we screen the possible ideas is much shorter, since we need a small amount of material, short processing time, ease of changing one material to another, easy to operate with one man, and that all allow you to have a shortcut from idea to screening, let's say from idea screening to concept development, where you start to make a value proposition. In addition, when you use a microcompounder at the initial phase of your R&D process, your overall R&D costs will be much lower, because you will be much faster. So if you combine all these shorter time and lower R&D costs, that means efficient R&D. When I come back to the question on the screen, the overall impact of microcompounders in the total rubber industry will be the speeding up the R&D process and lowering the barrier between idea to concept development. Do we have other questions, maybe? Oh, okay. Do you think microcompounding can contribute to circularity and sustainability aspects, which are recently considered the highest priority, global policies? Yeah, okay. Yeah, this is a very good, very relevant question, actually. Yeah, of course, there is plenty of contribution by different means. But let's take sustainability and circularity into consideration separately. When we think about circular materials, we should understand that we must use less amount of resources and then keep them in use again and again. And we need to delay the extraction of new raw materials. Right now, if we look how the world economy is, then you see that we are far from being circular, and we could say we are mostly linear. So how we can approach our circularity targets? When we focus on polymers, for example, recycling technologies pull attention, where we have to generate new and environmentally friendly recycled routes to reuse polymers to keep the economy circular. This means that we must spend more R&D time and effort on particular field. Moreover, we need to reconsider the existing polymeric materials to make them recyclable. This is so-called design for recycling, and all these steps need new polymer material and technology development, where our products, I mean Xplore systems, accelerate the total R&D process. From sustainability point of view, we can consider the use of bio-driven materials, or let's say bio-based materials, such as cellulosics, or let's say biodegradable polyesters. They are fully biodegradable, having low carbon footprint. However, we have to formalize them to adapt them to existing specifications. And sometimes we even have to develop new processing techniques to convert them into useful products. For example, if you take cellulosic materials, they are renewable. You can obtain them from industrial forests, but they are very sensitive against temperature. So it means they degrade easily when you go to high temperatures. Therefore, you have to process them differently, such as, for example, in water-based solutions, slurries, whatever. And then you face with different type of questions, different type of problems, like very high viscosity or unusual rheological behavior. So if I sum up, long story short, in the coming quarter, let's say century, we have to tackle all these challenging cases to come up with new products, new technologies in terms of circularity and sustainability. And as Xplore, we foresee these challenges to transfer them into opportunities to help the researchers by modifying our instruments accordingly. Okay, let me make it a little bit bigger on my screen. Okay, rubber compounding has been conventionally carried out using Banbury mixers for both lab and manufacturing for decades. Okay, however, the instrument from Xplore offers a different mixing geometry. How do you approach to scale up? Okay, very good. From lab to pilot scale and from pilot to production. Okay, this is yeah, very good, very how to say, yeah, actually we are familiar to these type of questions. Okay, yeah. Over the years, scientists have considered many approaches to scale up mixing process, and the goal was at that time to match the laboratory results at a commercial scale. So as a result, we have a lot of different scale-up routes, scale-up parameters, and we have from very simple to very complex approaches in terms of scaling up. But one of those methods, and the most acknowledged one, is the specific energy input approach that is based on the micro extruder. Therefore, our approach is based on the relevant shear conditions, which are essential for converging, or let's say for correct upscaling. This complex rheological model relates to our micro compounders with actual melt conditions, let's say melt torque, the shear viscosity, and the corresponding, let's say, shear conditions. In addition, you also can drive the mechanical energy input. All these parameters, together with the upscaling protocol, lead the researchers to the upscaling of the compounding process. Yeah, actually, I would like to make one point clear. We do not aim to replace existing Banbury mixers or Banbury mixing process with our compounding technology. On the contrary, we would like to position our technology as a complementary and a combined tool for the rubber researchers to go faster from idea to concept. I think this was the goal. Do we have any other questions, maybe? Okay. Cooling during the compounding of rubbers is a critical parameter due to severe viscous heat dissipation. Do you have a technical solution in order to keep the temperature under control during compound? Okay. Yeah, heat generation. Heat generation in rubber mixing is a well-known phenomena. Sometimes it's a well-known problem. In general, rubber compounds are poor conductors of heat. Although we have in some formulations carbon black, which is known to have some thermal conductivity, but most of the time, rubber compounds, if you compare with other type of materials such as metals, for example, they are extremely poor conductors. So when you shear a rubber melt or compound, and you generate a lot of heat. In our compounder, what's the problem if you have a lot of heat? So the problem is, first, you can initiate the crossing reaction, which is well-known scorch. Then if you have a scorch, then it's a problem in material quality, and even you cannot dump your material from your compounder out. In our compounder, there are two ways to keep the heat under control. One of them is air cooling option. Our barrel of the compounder is equipped with air channels. It's hollow inside. So where you can blow cooling air to control the heat. Most of the times, this is enough. Let's say most of the thermoplastic processes, that air cooling during the processing is more than enough to keep the temperature under control. But in rubber processes, depending on the rubber type and processing conditions, for example, such as RPM or temperature, when air cooling is not efficient, then we have other option, water cooling, that is operated with cooling plates. We have two cooling plates from the front side and the rear side of the compounder. They touch directly to the metal blocks. And in this way, you can easily keep the temperature under control. One other important fact in our, application or technology is our volume is 15 milliliters. So the amount of polymer, amount of rubber with respect to the whole metal block around the polymer is, very small. This means that the heat generated from the rubber is absorbed by a big mass of metal. So most of the time, this is an advantage to keep the temperature under control. Do we have any other question, maybe? Okay. Technical application-related questions. Is it possible to add liquids to the rubber in micro compounders? For example, processing oils. Yeah, of course. Without processing oils, I think it's nearly impossible to process rubbers. At least based on my experience, it's nearly impossible. Our barrel is vertically positioned in and it's liquid tight, as I already explained during the presentation. This helps you to add liquids from the top of the compounder directly into the melt. Normally, we use a syringe, or you can use a pipette to introduce the liquids. Or if you want to dose liquid, then you can use a small pump, which could be located to the top of the, compounder from the feeding copper, or you can directly put a pipe to one of the feeding ports directly to the compounder. So the answer is yes, it's possible. Okay, we have a rubber material that is sensitive to oxidation. Yeah, okay. Can you prevent oxidation of the compound while processing in a micro compounder? Yeah, okay. Some of the rubber material, they are really, sensitive against oxidation. So yeah, in most of the cases, you need to use some processing aids to overcome that problem, such as antioxidants, such as, yeah, for example, in combination with oxidation and heat, can severely damage the chemistry of the molecules. Then you need to take the temperature under control, or you need to increase the let's say, no, decrease the viscosity of the material by using some processing aids, such as internal lubricants, maybe. But these are at the formulation side. At the sample preparation side, yes, we have a solution for it. We have an inert gas supply to the compound, to the barrel of the compounder. There's a pipe coming from the side of the compounder inside, directly inside to the barrel. You can purge your barrel, then you can purge oxygen using pressurized nitrogen, or even better, you can use argon to remove or to purge the oxygen. So yeah, we have a solution for these, and you can minimize the oxidation of your material during sample preparation. Other question? Okay. Is microcompounder only dedicated to research facilities, or can it be also used for production purposes? Yeah, okay. Yeah, interesting question. I can say this is, I cannot say actually this is only for research purpose, but I can say it's mostly used for research by the researchers. But for example, our bigger compounder, 40 milliliter compounder, can be used to prepare some custom designs. For example, extremely high-end, low series production. And yeah, our machines are designed to work for let's say 24/7 conditions without any issues. So yeah, but if you also let's say ask me what the percentage of the total sales to produce polymer parts is, yeah, the rate is not really high. So the answer is yes, it can be used for production purposes. But you need to think of that they are small compounders. And yeah, I can add one more thing, Param, if you, I just remember. On the other hand, we also know that our machines are sometimes used to make regular quality control in thermoplastics, or in even rubbers, by the help of the rheological software, or just a torque readout. You can quickly monitor the change in viscosity of your products using a small amount of sample. So I can also combine this with the question. Okay, we are located in India and active both in India and Southeast Asia. How do we reach you? Is it possible to make demo runs with our, yeah, okay. Yes, of course, it's possible. Yeah, first of all, I would like to emphasize that we are a globally active company. We have a well-established agent network and distributor network as well, all over the world. And if I come down to that question, yes, we have an agent in India and agents in Southeast Asian countries. You can find the contact information of our agents on our webpage, or if you can directly contact us, we can bring you to contact with our agents. If you want to make a demo trial, you can visit us in our demo lab in the Netherlands. You are welcome. And there we have a technician and available systems. We can run your material. Yeah, because we know the best way to convince a researcher, who are our customers, is to show the abilities of our machines with the results of demo trials. If you are not able to come to the Netherlands, you can send us your materials. Of course, we sign an NDA and we process your material. we can ship you your process material back to you, or even we can make some videos. We can make some live sessions that you can also how to say observe how we are running your material. It's possible. You're welcome.
Dr. Gurap, I think you are going to be in India, right, for the IRC? Are you going to exhibit in the,
Yeah, exactly. I think in 2 weeks, the week starting with 20th, there will be a big show, and there will be a conference on rubbers organized by Indian Rubber Institute. It's well known, IRC, huh? And we will be presenting over there. Me and my colleague, the Professor Kodal, is going to give some how to say presentations, and we will be showcasing our rubber compounder over there. And our Indian agent, Venture Technologies, will be representing Xplore. So if we have audiences who is planning to visit IRC, they are welcome to our booth. Then we can also discuss just in front of the machine, and they see how the machine looks like. They can feel it, you know. It's always good. Do you have questions? Okay. Okay. We're working with both black and non-black compounds. Therefore, we have 2 Bunbury type mixers. Okay, in the production, yeah, or in the lab maybe. If you want to have your machine micro compounder, do we also need to buy 2 machines? No, they need to buy 5 machines. No, it's a joke. Yeah, okay. Yeah, I understand the question actually, because from also my personal experience that once you use carbon black with your instrument, later on cleaning becomes a real issue. Yeah, if you shift from black compounds to non-black ones, yeah, this is a well-known problem at lab scale and also during the production. However, in our system, yeah, this is prevented by easy cleaning of the machine. Since the barrel is completely closed and only feeding can be done from the top opening, you do not have too much dust contamination problem. The other advantage is when you use a cleaning or let's say a purging compound to clean your machine, since the screws are fully intermeshing that I showed already during my presentation, maybe you can go back in the YouTube channel. The screws help the cleaning compound to remove all the residues because they are self-cleaning. And finally, you can easily open the barrel if needed, because we have 1, 2, 3, 4, 6 bolts. You can open the barrel and you can use a steel brush to take everything off. So it's not difficult. Okay, can we use fluorinated elastomers with your machine macro compound? Yeah, okay. I think the real question is if our machine is resistant to chemicals, because yeah, as you know, fluoroelastomers are sometimes we think that they can generate some, let's say, corrosive components which could interact with the metal on your machine. First of all, the barrel of our machine is made out of a special type of steel. It's very strong. The hardness more than 60 Rockwell-C, I think 63, 64 for Rockwell-C, it's like diamond. Therefore, mechanically, it's nearly impossible to damage the barrel. And the material we use is resistant to a variety of acidic and basic components in a broad range of temperatures. So therefore, I can confidently say that our machine is resistant against fluoropolymers. We also know that from thermoplastics. We have quite a number of customers. They are using fluorinated polymers, Teflon-like of stuff with our machine, and we didn't see issues. Of course, the proper cleaning is the key. You need to maintain your workhorse to keep its condition at a level. So normally we advise our customers when they use some potential, let's say, acidic or basic materials, then we advise them to neutralize the barrel after the use. So if you maintain properly, nothing will happen. You showed some examples from your work with CNT, carbon nanotubes. Yes, yes, yes. CNT are known to be expensive additives. Yes, they are. For example, how much CNT is needed to make one batch of nanocomposite? Okay, a good question. Let's calculate together. The barrel of MC15HT, it means 15 milliliter compounder is 15 milliliter. And if the density of the compound is around, let's say, 1 grams per milliliter, then your compound per batch will be 15 grams. If you load, let's say, 3% carbon nanotube, then you need 15, 3%, 0.45 grams of carbon nanotube per batch. And let's say you repeat one batch 3 times to get an average result. Then you need around 1.5 grams of carbon nanotubes to come with some amount of material. And if you would use a conventional type of laboratory mixing device, for example, I think the minimum is around 350 milliliters, then you would at least 10 grams per batch. So if you use a macro compounder, you need really a small amount of carbon nanotubes, 1.5 grams. Yeah. Okay. In the videos, you showed that you were extruding in a strand form. Yeah, it's spaghetti-like structure. Okay. Is it also possible to extrude in sheet form? Yes, it is a very relevant question. Yes, it's possible to extrude in sheets form. We have a sheet extrusion die. You can also say it a film die, but normally the thickness is not too thin. For rubbers, it's thick, let's say 2 millimeters, 3 millimeters. Even we can arrange it. So you can make stripes out of rubbers, and you can extrude that stripe directly to a container, or as I showed in the videos, that we have also a mini conveyor belt. You can just extrude that stripe on that conveyor belt, and you can take it for further analysis. What would be the highest filling ratio that could be achieved with Explore machine? Highest filling ratio. Yeah, actually it depends. It depends on filler type and rubber metrics, but I could give you an example. For example, we were able to prepare 200 PHR carbon black filled EPDM, but please think that carbon black and EPDM, they are compatible. They like each other. If you consider silica with EPDM, you need to make trials. But we have a very high torque to compound high content of fillers into rubbers. The answer is the highest filling ratio depends, but it's really high.
Okay, that's all the questions we have.
Okay.
Thank you very much for addressing all the questions. Before we end the session, I have a couple of additional points to touch upon. It looks, based on the presentation and also that the benefits that I see, it's a very useful instrument for the rubber people, particularly in the developing compounds, also in the product development itself. How is experience so far in terms of the utilizing the in the non-tire industry, this instrument?
Of course, we are not limited to only tire or only non-tire. Actually, our compounder is if you have high viscosity and you want to mix something who has high viscosity with something, then you need that microcompounder. So it's not limited to tire, or it's not limited to non-tire. So it's just broad.
And so how many instruments being currently in use around the world now in rubber and tire industry? Probably a couple of hundred.
Yeah, this is the most difficult question. Yeah, okay, we have, because then we need to go back till, because the company Xplore comes from DSM, so you need to go back, let's say 30 years. I can say too many.
Okay.
For 500 maybe, yeah, you know, a lot of machines. They are still running. Yeah, some of the machines, they are still running. We sometimes see machines, they are coming for, let's say, yeah, small maintenance, and the barrel is like in first day the mechanical parts. So it's a well designed, robust system. Yeah, really.
So less maintenance issues, right, in this instrument?
Exactly, less maintenance issues, because, yeah, to be honest, we don't want to have, let's say, the hurdle of maintaining the devices that are on the field. That's why we are designing our machines, which you don't need to maintain them, you know. But if needed, of course, we have a well-trained service team, and we have a well-trained, how to say, agent network. So if needed, of course, we can serve.
Yeah, fantastic. Okay, I think that's the end of the session. I'd like to ask you to give final remarks to the audience, please.
Yeah, okay. Yeah, what I would like to remark, that we are at Xplore dedicated to our core business, supporting scientists and researchers, and by developing high quality and robust microprocessing equipment. We want to be the front runner of the manufacturers of, let's say, micro processing instruments, focusing mainly on, as I already said, high viscous materials, such as rubbers. We respect the challenges and creativity of the scientists, and we want to provide them with innovative, high-quality screening tools to develop novel formulations, novel recipes that possibly serve sustainable materials and circular technologies for the future. Yeah, we believe that our rubber microcompounder will serve as a remarkable instrument to sustain effective R&D. And I would like to invite the researchers who are interested in our product portfolio to run on-site demo sessions. They can also reach out, explore from our website or from our social media. And I also would like to thank all our audience today for their interest in a Q&A session. And I thank you for giving me this opportunity to talk about our rubber microcompounders and its applications. Thank you very much.
Okay, thank you very much, Dr. Gurab. That's the end of the presentation, and I hope to see you in the IRC in Bangalore in a few weeks' time. Thank you very much.
Sure. You are welcome. Bye.
Bye. Okay, so that's the end of the presentation and today's episode number 41, focused on the microcompounders for the rubber R&D. Introduction and case studies by Dr. Gurab. I'm hoping that you find this session useful. You can watch this session in record format on YouTube at Technobit channel. Feel free to check it out. Not only today's episode, but also you can watch all the past episodes as well. Okay. Then I see you in the next episode. Thank you all for joining today. Bye bye for now.